Morning, guys. So over the last 2 days, we started looking at the beginnings of Chapter 1. We started introducing, I just keep drawing this summary diagram for you so you can help internalize it here. We introduced the concept of the mole. The mole represents a box. Inside the box has a huge number of particles. Yesterday we had earlier talked about this bubble here being number, but yesterday we had to separate it. Well, depending on what's inside my box, it's either molecules or it's either atoms. I'll do a practice question with you just to do that there again. But nonetheless here, 1 mole was defined for carbon. It was an Avogadro number that you needed inside. That got you over to number. Depending on what's actually inside your box, we can actually go to mass. So mass, the conversion's name is called molar mass, but we're going to use our PT, our periodic table. Make sure you are using your IB8 periodic table, which has 2 decimal places. And yesterday we also said for specifically a volume. Later on we're going to look at another volume, but for this volume here, the restrictions are we're only looking at gas volume, the amount of space that your particles spread into at our standard conditions at STP. That conversion there was called molar volume. And in that case there we can say 1 mole was 22.7 decimeter cube or liters. We'll come back with the ideal gas law lesson later on to figure out if I'm at a different temperature, different pressure, what that conversion should actually end up being. So let's just have a look at one practice question and then we'll move on with today's lesson. First question here, I just want you to practice how many fluorine atoms in 56 decimeter cubes of COF2 gas. So as always, what I want to start off with here is I have my map. I want to figure out where my number goes. So I start off with the number here, 56 decimeter cube. The units will give it away a lot. This decimeter cube here is a volume. I only so far have 1 volume bubble. I'm looking starting from here. And I'm interested in getting a counting number of atoms. Well, number of particles is way over here. And in this case, I'm interested in just counting just the F parts inside your compound. So I'm interested in getting to your atoms here. I definitely don't see any connection here, so I can't actually just jump over that way. What I need to do here is I need to first go through moles. Unfortunately, this guy here itself is a molecule. When you end up using Avogadro's, it doesn't go down this pathway, which I want to. It's actually going to go down the molecule pathway first, and then I need to say, if I have 1 mole, how many F atoms there are. Right? But so be it, I'm predicting there should be 3 conversions. At the end of the day, I want to know how many F atoms, or atoms of F. Start off with the number given, if you're completely lost, 56 decimeter cube. My first conversion will go volume to moles. So let's get rid of the volume unit, let's get rid of decimeter cube, let's just go to moles. Let's go to how many boxes. Then when I use Avogadro's number, like I said, because this is a molecule, I'm going to get rid of the moles on the bottom. Unfortunately, when I use Avogadro's number, I'm stuck with molecules on top. I'm stuck over here. And now what I want to do as a last step is I want to say, okay, fine. If I have just 1 molecule, how many, in this case here, F atoms I need. Again, if it's your first time doing this here, it's really weird because what I'm going through, I'm just canceling out units. Right? I'm not actually punching the numbers in just yet. The numbers should be the easier part. So let's give me one true relationship. The moles to decimeter cube, oh, we needed to use molar volume. 1 mole is 22.7. When there's a 1 with a mole, there should be a 22.7 decimeter cube. For the next one here, for 1 mole, there should be an Avogadro number. When 1/6 of the mole, there is now an Avogadro number of molecules, 6 × 2 × 10 to the 23. If I have 1 molecule, so if you imagine 1 car worth, sitting inside of this blob here is just a bunch of these cars of COF2, COF2. I don't want you to just give me a count of how many COF2s I have. I want you to count 1, 2. 2 F atoms for every car that you have. So I have 2 fluorine atoms. That's a small counting number, so that's exact. Numbers on top you multiply, on the bottom you divide. So I would type this in here, 56 times Avogadro's times 2 divided by 22.7. Double check my numbers. I got here 2.97, so let's make it 3.0 times 10 to the 24 F atoms. Right. If this is a paper 1 multiple choice question, obviously you don't need to show your work, but definitely by showing these conversions here, it'll make sure you're multiplying the appropriate numbers and also dividing the appropriate numbers as well. Today what we're going to do is just switch gears a little bit. Okay, we will come back to this diagram. I do have to add for you 1 more bubble with concentration later on. But just for a quick break here, we're going to study this sort of mole to mass conversion in just a little bit more detail, framing in a slightly different way. So that's sort of the connection to what we've been doing so far. We'll come back to this summary diagram. Today's lesson, I want to start off with a guy called percent composition or percentage composition. As the name suggests here, it's the composition, it's what you're made up of, and it's the percentage, it's the fraction, it's the proportion of the elements. So percent composition here, it's the proportion of, I'm just going to use a generic term here, species. That could be an element, it could be a grouping, right? It's a proportion of that thing, that substance in your compound. And unless otherwise specified, we're going to be doing this by mass. So it's a mass percent, it's a mass of this element within the mass of the compound, or it's the mass of this grouping, again, within the compound. You could actually do a percent composition using volume for volume, but that's more so a concentration thing we'll see later on. Right? So let's just start off here. This is the easier way of asking the question because I already know what the compound is. Let's take the molecule CO2 as an example. In chapter 4, we'll come back and we'll figure out how things are actually bonded. But I know this CO2 here is made out of 1 carbon and 2 oxygens. Let's look on our trusty periodic table. Let's make sure we know the masses. So carbon itself was 12.01. Oxygen on our periodic table was 16. What I can do here is I can figure out, well, what's the total molar mass? If I just add those numbers up, 16 times 2 plus 12.01, the total molar mass, M, is 44.01. Again, it's best to say no units because this one here, so no units, since it's relative to C12 being 12. I had assigned the carbon 12 isotope, that version, as 12. That's where I came up with my atomic mass unit conversion. And now all my numbers are relative to carbon being 12. So this one here is 44. You probably guessed it here. Can you find for me the percent carbon or the percent oxygen? In this case here, well, I happen to have one C atom amidst the CO2. All you're going to do is you're going to take, well, my 1 carbon weighs 12.01. My total mass is 44.01. Let's figure out what that decimal is. Because it is a percentage, I'm going to be multiplying it by 100 as well. 0.2729. You scale it up by 100. So 27.29% by mass is actually carbon. Right? So about a quarter's worth of this carbon dioxide's mass here is the carbon element within the whole thing that weighs 44. Now to get oxygen here, you have 2 ways. Because there's only these 2 elements here, whatever is not carbon has to be oxygen. So I could actually just go 100 minus this 27.29. If you didn't want to do that, in case I got the carbon wrong here, I'm just going to show it to you with the oxygen side. Let's say I have 2 O's. Careful, that looks like 20 there. But I have 2 oxygens. Each oxygen weighs 16. Again, that is not diatomic. It's not because it's elemental. This oxygen is being stabilized with carbon, but it has happened that I have 2 oxygens. I do the division there, 32 divided by 44.01. This gives me here 0.7271. Again, by percentage, that's 72. That's the other proportion. If you add those 2 up here, this one here works nicely to 100%, as it should, right? Because this one only contains C's and H's, C's and O's. Depending on how you do your calculation and how you round your percentages, sometimes when you do the addition, it might add up to 99.99, 100.01. That's perfectly fine because it's just rounding and truncating of the decimal. So it's the easier way of asking the question because I already know what the compound is. Just getting you to practice here. Let's go to our friend. Find the percentage water in copper 2 sulfate pentahydrate. Hopefully we'll get a chance to actually use this chemical in the lab. It's a nice blue color, right? So copper 2 sulfate pentahydrate. That's why we had to practice a lot with the naming so that we can actually get the formula correct. So if you can practice it for yourself here, copper 2 sulfate, copper it's using its +2 charge. Sulfate is SO4 with a -2 charge, so CuSO4. Make sure you memorize your polyatomics. Make a note of this here. Memorize the polyatomics. Alright, so CuSO4. Then I have a pentahydrate, usually in an ionic compound like this, metal with a covalent polyatomic grouping here. Usually we don't get prefixes. This time we are getting a prefix because it tells you how many waters there are. So this is .5 water. So I know the CuSO4 here is made out of a bunch of these blobs here. Cu, the SO4 blob, it's positive, negative. It's going to be a huge lattice. It's going to keep repeating in 3D space. But relatively speaking, for every 1 Cu, 1 SO4, there happens to be 5 waters, like a wet sponge, soaked into the pores amidst the CuSO4. So, especially when I'm dealing with molar mass, I actually want the molar mass of the entire thing. Now you'll notice that in the definition I said, oh, when you find the percentage, it's the proportion of that species. You notice I wasn't too general here. I didn't just say proportion of the element in a compound, because I could also do a percent composition. Well, this isn't an element, but I can still say what's the fraction that is water. You could totally do percent H or percent O, just like we did earlier. But this time I want you to keep that grouping together. That's why sometimes in the definition, we want to keep it a little bit more rounded, a little bit more of an umbrella, so I can capture more of it. Don't be too specific if I don't have to be. So let's try it out here. Again, I would normally not show this work here, but basically I'm going to take Cu, I'm going to take the sulfur's mass, 4 times the oxygen's mass. I'm going to take 5 times the mass of water. Right, this is the math that I'm actually typing in. Double check your numbers on your data booklet here. For copper, careful not cobalt. Sometimes I get people look up cobalt instead. 63.55 plus sulfur. Sulfur is 32.07. I'm going to have 4 times oxygen's mass, which is 16, plus 5 times, you can just do water's mass by itself, 2 times 1.01 plus 16. I'm going to add up all of those together. Double check my numbers. And I'm getting the total molar mass is 249.72. Again, best to say no units. So this thing here as a hydrate, this is called a formula unit, right? Because this is your Lego block. Formula unit. This is your Lego block in your ionic lattice. I know your lattice will be trillions and trillions and gajillions of these particles, positive, negative, alternating. But my formula unit, my ratio, is given by 1 Cu for every 1 part CuSO4, and there's actually 5 parts water. So that's the total molar mass. It shouldn't be that hard. If you wanted to, for completeness sake, you can say, what's the percentage Cu, what's the percentage sulfur and oxygen here. In this question here, they're just asking you percentage of water. And pretty much it should be, well, my hydrate has 5 waters. This is actually an easy way to actually figure out how many waters should there actually be. But I have 5 waters amidst my hydrate, which is CuSO4.5 waters. I would prefer for you to keep the water together, because as a hydrate, it's soaked up a grouping of water. And also, it's a little bit hard. If I said percentage oxygen, there's some oxygen just in the sulfate, there's some oxygens there. The oxygen way would get a little bit messy. In this way here, we keep track. Nope, it's just the water grouping. 5 times the 18.02 that water has, divided by the total molar mass of 249.72, again, times 100 to make it a percentage here. Give or take a little bit of rounding. I'm getting the fraction of this being 36.08. As you're doing sig figs here, it's based on the sig figs of the problem. I'm dealing with a 4 sig fig number. This 5 is an exact number because I'm scaling up by exactly 5 of them, not 4.9, not 5.1. This one here is a 5 sig fig number. If I go 5 times the 18, I don't quite get up into the hundreds yet, so this would still be 90 odd, 90.1, something like that. So that's 4 sig figs. So 4 sig figs is fine. If I happen to have 6 waters and this ended up being like in the hundreds, that might be 5 sig figs, 5 sig figs. You can keep your answer to 5 sig figs as well. So you just follow your rules here, just simple multiply, divide again. As I've been saying, this is sort of the easier way of asking the question, because in both of these cases, I had already known what the compound is. So if I know what CO2 is, it's pretty easy just to go, okay, well, here's the total molar mass, and here's that fraction of just this part, or just the water part. Usually, though, I don't know what the formula is. What I'm going to do at the end of this lesson here is I'm actually going to flip this question around. What if we actually go and do an experiment? And what if the sort of the machinery or the results that we get, what if they give me these percentages? What if they say, oh, my sample is actually 27% carbon, 72% oxygen? Would you be able to take these percentages and actually go back and figure out, oh, that means my compound has to be CO2 because that's the proportions inside the CO2, not CO, not CO3, not C2O, not any other ratio. So what we're going to do here is we're just going to switch the question around here. We're going to flip the problem from if I know the percentages, let's see if we can work our way back to actually find what's called the empirical formula. What numbers do I actually need in the real compound if these are the percentages that I've got? This way here will seem a little bit hard. Okay, so I'm just going to step our way through here. This is our main term for today. We're going to call this one here the empirical formula. And it really is just the opposite, just the backwards of what we just did there. So empirical formula, I know when I was in Chem 11, I was always scared away. What does it mean empirical? Empirical just means experimental. So when you actually go in the lab and you actually got these numbers, what you're trying to do is you're going to try to take, these ones here are from your experiment, you're taking your numbers, you're trying to get back to a formula. You're trying to get back to the symbols, you're trying to get back to the ratio. So in this case here, your empirical formula is the simplest whole number ratios in your compound. So really, we're just trying to get from some sort of percentage information. I can run an experiment empirically, I can determine that, and this is going to get you your EF, which is your empirical formula. Empirical formula is a simplified ratio. It says, oh, CO2, for every 1 C, the ratio is 2 times oxygen. So as you first look at a question here, it may seem a little bit scary, but it's always going to be the same sort of techniques here, same sort of brute force method that we do. Let's try it out here. A sample contains 8.40 grams of carbon, 2.12 grams of hydrogen, and 5.60 grams of oxygen. The question is just going to read, find or calculate the empirical formula. Right? So again, let's just break this question up. We're looking for the empirical formula. We're looking for the simplest whole number ratio. I know I have 3 elements. In order here, I have carbon, I have hydrogen, I have oxygen. What I'm interested in is the actual numbers, the CX, HY, OZ. What's the proportion, what's the ratio between how many C's to H's or C's to O's? So I'm interested in finding the XYZ, which is represented by these relative amounts. Now these relative amounts here, they're not actually giving to us as percentage, but if I really want a percentage, it's not that hard. The total mass here would be some 16, 17 grams or so, 8 divided by 16, 8 divided by 17 or so. That would give me the fraction. It's actually helping you out a little bit here. I already have the percentages, and they're actually already expressed in terms of masses. So if we can, I'm just going to start off with a picture. So I have a sample here. I'm expecting to be about 16, 17 grams total. I have some half of it. 8.40 grams is actually carbon, so C for carbon. I have 2.12, so less mass of it. Realistically, the sample may not be fully isolated like this, carbon just on one side, hydrogen on one side, but just for simplicity, I'm just keeping it like that. This case here is now going to be 2.12 grams. Question here, when I put H, should I put H or should I put H2? Think about when was it H2? It was those diatomics, is when it was elemental. Sure enough, in this question here, I have no clue how many H's, what the number should actually be, but this is definitely not H by itself. So this is just going to be the plain old H, not H2. So make a note to yourself here. It's not diatomic, it's not elemental, it's not it by itself. And in the same way here, 5.60, although oxygen would have been O2, this isn't oxygen by itself. This is being stabilized by the carbons and hydrogens. It can just be grams of oxygen. Again, just for your thinking here, if I add up these masses, 8.4 plus 2.12 plus 5.6, my whole sample here is 16.12 grams. So that's total. I don't really need that number, but that's just for reference. In that case there, like in the next problem, when I give you percentages, you might need to take the percentage and actually calculate the mass. They've actually helped you out with one step. But by knowing the total mass, I can say, well, about 50% is carbon, 2 out of 16, whatever that is. About 12% or so is hydrogen. These mass numbers here are actually giving you the percentage information. In fact, to get from percentage over to empirical formula, one of our steps is to get the mass numbers. So they've already sort of helped us out here. They've already given you the masses. So again, this part here will feel very systematic. What we're going to do is we're going to set up a couple rows. I'm going to set up a row for carbon, 1 row for hydrogen, 1 row for oxygen. So far, I'm going to start off with the experimental numbers. They found 8.4 grams, 2.12 grams, and 5.60 grams for each of these elements. why can't I, at this point here, just come along and just say C 8.4, hydrogen 2.12, oxygen 5.6? Well, first major question here is, in the periodic table, these have different mass. This has a molar mass of about 12, this only has a molar mass of 1. So although these are all measured in grams, the grams mean something different for each element. So here are your steps. What we're going to do is we're going to divide out the molar mass. Let's put them all on a level playing field. Let's make them all counting numbers so at least we can make a fair comparison. The first one is divided by 12.01. Hydrogen is divided by 1.01, just one hydrogen. And oxygen is divided by 16. All right. In this case here, I'm going to tell you can be a little bit sloppy with sig figs. We'll see why in just a second here. So keep a few extra decimals. I'm getting 0.6994. 2.12 divided by 1.01. I know divided by 1 doesn't really change much, but still type that in. 2.099. 5.6 divided by 16 gives me, oh, that's a nice number, 0.35. All right. If you're really, really astute here, you'd actually realize what I've just calculated. By dividing out its own molar mass, I've actually found the moles for everything. You can see that conversion here. What would happen if I took a grams and I actually, I want to get rid of grams and go to moles? This one here would have had your molar mass. Grams cancels with grams. Grams divided by this number of molar mass would end up giving you moles. So just to confirm for you, these ones here are actually moles. We've taken care of the problem here. Everything weighs a different amount, so I need to divide that first. At this point here, realistically, I could really go C, 0.6994, hydrogen 2.099. It's just not very nice to look at. What I want to do is I want to simplify it. I want to, like fractions, make it the smallest whole number ratios I can. And what we're going to do that seems a little bit strange. What we're going to do is look at all these moles that we have. I want you to take a look at which is the smallest number, and I want you to divide everything, scale everything down by the smallest number. In this case, as the smallest number is 0.35, I want you to this time do the same operation, divide 0.35 on all three numbers. What that does is it knocks one of them definitely to a 1, a number divided by itself, and it helps us rescale the other ones. Here's why I wanted to keep a few extra decimals. I don't want to accumulate rounding errors. I get 1.998, 2.099 divided by 0.35. This gives me 5.997. All right. So because I did the same operation, divide 0.35 by all three elements, the numbers are still by ratio exactly the same. Now at this point here, you need to use your judgment. In this case here, as a general rule, I don't want to do crazy rounding. If this number were, let's say, 1.5, we're in math class, you can round, 1.5 is just 2, that's easy. The trouble is, if I do a lot of rounding in just one element, and I don't have a similar rounding in the other element, it would actually skew my numbers a little bit. So, as a general rule, let's write this down in words here, keep rounding to a minimal. Because I want to preserve this ratio, it is really 1.998 to 5.997 to 1. So if it was 1.5, I'm going to tell you how we do that later on. I don't want to do drastic rounding in one chemical without that same drastic rounding in others. Now, in this question is not too bad. Practically, you'd say to me, yeah, 1.98, yeah, that's pretty close to 2. That's not that bad in terms of rounding. 5.997, yeah, that's pretty close to 6. So because the rounding is reasonable, I can do that there. Don't leave it like this. So you can actually backtrack. You can say C2, when carbon is a 2, hydrogen is actually a 6, and oxygen is a 1. Chemists are lazy, so you can just drop that 1 there. This is now called your empirical formula. The simplest ratio in your compound has 2 parts carbon, 3 times as many hydrogens, and half the number of oxygens. As I mentioned here in math class, if the number at this point, if it had come out to you as a 0.5, math class 1.5 to 2 is not that drastic. But in this stuff, it would be. You would have skewed the carbon so much so that your empirical formula may not actually be the C2 that you wanted. So the question here is, how else can I minimize that rounding without actually affecting the overall proportions? And here, again, it's a judgment call. So at this point in your work here, if your endings end in 0.5, is there another way I can make a 0.5 a whole number without rounding? Hopefully you're able to say to me here, well, 0.5 is just a half. Let's pretend to scale everything up by 2. That way I can times 2 for the one I'm trying to round, I can times 2 for the other one, and at least I'm going to preserve that ratio. What if the ending was a 0.33, or what if it was like a 0.66 or 0.67? You'll recognize in terms of your fractions there, those ones there are actually thirds, so the scaling factor is actually multiplied by 3. I can actually scale it up by a whole unit, a whole number, and it'll actually give me, without rounding, preserve that ratio. 0.25, 0.75, those are quarters, so you can scale that up by 4. If it was 0.2, 0.4, you can scale it up by 5, so on and so forth. So that's just a judgment call here. You do want to keep the rounding to a minimal. I don't want to skew one chemical in relation to the other ones. I want to preserve the ratio as best I can. So we're going to see that practice in our last example for today. Let's start off here, new example. A hydrocarbon. Right. Oh no, there's a new word there. That's actually an organic family, very simple organic family because it only contains 2 elements. The hydro part tells you only contains hydrogen, right? That's the hydro part, and oxygen. So that's a family that just has C's and H's. A hydrocarbon contains 81.7% carbon. I want you to find, sometimes they even sound complicated, they're going to say deduce. Okay, deduce is just determine. Okay, deduce the empirical formula. See if you can take this experimental evidence, experimental numbers, and tell me what the ratio should be. In this case here, I know it's a hydrocarbon. I know it's going to be C something, H something. You can even say HXCY like that. The order doesn't matter, but it's just looking at organic compounds. We typically have the carbon part before the hydrogen. I'll give you one small hint, and I'll let you try it out. So we have a sample. This time you'll notice, different from the earlier question, we're actually not given masses. We actually want to go straight from percentage over to the empirical formula. We saw that in our work, percentages weren't that easy to work with. I actually needed masses so that I can divide out the mass in one step. So what we want to do here is we want to come back up with some masses. I actually have no clue the sample that they tested. It could have been 10 grams. It could have been 100 grams. It could have been 1,000 grams. I don't know. But what I'm going to do here is I'm going to assume, let's pretend we now are looking at a 100 gram sample in front of you. What's so special about 100 here is percentage works really nicely with 100. What is 81.7% of 100? Well, that preserves the number, 81.7, and now we have grams of carbon. You've been able to convert percentage over to grams pretty easily. Now, it would totally work if you put 200 grams, figure out what 81.7% of 200 is, put those numbers as well, but why do that? Just take it out of 100 because it's easier. They haven't told you hydrogen. How am I supposed to know that? Well, again, because this one only contains C's and H's, I'm just going to go 100 minus 81.7, and this gives me here 18.3 grams worth of hydrogen. So if you want to pause the video there, try it out for yourself. Do the divide molar mass, divide out the smallest number. You're going to find that the ending is going to be one of these endings, a half, a third, or a quarter. You need to scale everything up, and then you just quote me the empirical formula. So having a look here, assuming you pause the video and just check your work here. Let's take these masses, 81.7 grams, 18.3. It's always very systematic. The first problem to take care of is divide out their own molar mass. These are not the same mass, so it's not a fair comparison so far. 81.7 divided 12.01 gives me here 6.803. Be a little sloppy with sig figs. The reason why is because I don't want to accumulate rounding errors. The other reason will become very clear as we do this. 18.119. These ones here, if you're thinking about it, this one here is actually moles. And now what we're going to do is we're going to divide out the smallest one. The smallest number was a 6.803. That's going to knock one of them to 1. What's 18.119 divided by 6.803? This gives me here roughly 2.66. By being a little sloppy with sig figs here, I made sure to not accumulate rounding errors. Again, in math class, 2.66 rounded to 3 is not that drastic. However, in this empirical formula stuff, if I am doing that rounding just in hydrogen, I may have skewed the hydrogen ratio carbon proportion. That may not actually be my real compound. Is there another way I can scale that to a whole number? Hopefully you can recognize, well, 0.66 is close enough to 0.67, and that's a third. Let's imagine scaling both numbers up by 3. That way the carbon is 3, and we have 2.66 times 3 should give you an 8. And there we preserve the ratio, 6.803 to 18.119 in the compound C3H8, which is actually propane. Right? Sometimes you need to do that last rescaling. It really depends on the numbers that they give you. So practice through your worksheet, try out a few of them, draw pictures if you can, convert to mass, and do the systematic procedure. Divide out the mass, divide out the moles. The other reason why we can be sloppy with sig figs is ultimately we're ending up with a simple whole number as well, just the one digit. So you don't need to worry about following sig fig rules. So just practice through your questions and let me know if you have any questions. Thanks, guys.